thank you. Thank you for the introduction, Constantine, and welcome everybody to this webinar. My name is James Green, and I'm a software scientist at Molecular Simulations from First Principles, or MS1P, here in Germany. And in my talk, I'm going to first give a short introduction to FHI-aims, and as well how we at MS1P fit in with this. And then I'll go on to give a brief overview of different methods for electronic accepted states in FHI-aims. So the first thing that I should say about FHI-aims is that it's really a community project, a community code. So there have been contributions from over 150 people in 20 years all over the world. And really, the code wouldn't exist as it is without these people. So thank you very much to everybody you see on the screen, plus potentially others as well. So how we're organized. So like I say, FHI-aims is a community-based software, community-based code. It's hosted on an open development platform on GitLab. So there, once you have access to the code, anybody can contribute. And really, new physics and new methods are constantly being added by different scientific groups around the world, as you saw on the previous slide. And then how MS1P fits in with this. So we are a German nonprofit society with 5 employees plus an executive board. And we're essentially here to support this FHI-aims community and the code. So we're responsible for licensing FHI-aims both to academia and to industry. And once you have a license for FHI-aims, you can register on the GitLab and have full access to the source code plus wiki pages and issues and things like this. And you can also download the code or release versions of the code at our website, or at the FHI-aims website. We're also responsible for help with code stability and integration. So when a scientific group adds one of these new methods, we help to try and integrate it with the existing FHI-aims software to ensure everything is still working correctly. And we also help fix bugs that come up during this process and otherwise as well. We also provide community support, and one of the main channels we have for the community is a FHI-aims Slack channel. So at the moment, this has around 1,000 people on it, and generally this is the first port of call. If someone has problems or questions with FHI-aims, they can post a question there, and generally either one of us at MS1P or someone else from the FHI-aims community will be on hand to help out. We also help with documentation, webinars such as this one, and tutorials such as the one that will be tomorrow. And as well, we collaborate with industry partners as well. So I mentioned the website on the previous slide, and this is where you can get the code. And you can also see a wide range of online tutorials that we have for FHI-aims. So at the moment, I think there's more than 30 tutorials, and these are constantly being added to, primarily by people who have developed new methods and want to explain to others how these methods work. And we at MS1P also add and edit some of these tutorials as well. And I'll mention some of these tutorials when I get onto the part of the talk about accepted states. As well, on the website, you'll see at the moment a link to a preprint of the FHI-aims roadmap. And this is on arXiv and has more than 30 sections with over 200 authors, essentially describing the last 20 years of development of FHI-aims, plus where it will hopefully go in the future. And I'll touch on some chapters of this roadmap paper a little later on as well. We also have a YouTube channel, which maybe some people are watching on, where we also have introductory videos, tutorials, and recordings of this webinar series and other series we've run. Okay, so now that's kind of a quick overview of the infrastructure of FHI-aims and how MS1P fits in with that. So now onto the code itself, and I'll just briefly describe essentially the philosophy and the design principles that went into creating FHI-aims. So from the outset, the vision was to create a software that is capable of conducting quantum mechanics-based simulations of real complex molecules and materials and their properties without a priori precision and accuracy limitations. And there's kind of three key points to this. So the code should be versatile, so capable of simulating both non-periodic or molecular systems on the same footing as periodic or material systems. It should also be precise and accurate, both for all electron density functional theory and correlated methods beyond DFT as well. And finally, it should be scalable from laptops to large HPCs with thousands of compute nodes or thousands of CPUs, and from tens to thousands of atoms. And a key design choice that was made in trying to fulfill these aims was to use numeric atom-centered basis functions. So as many people everybody who's done some kind of quantum mechanics simulations before knows, we generally represent a wave function, in this case electronic wave function, as a basis set expansion in terms of basis functions phi-i. Now in many molecular electronic structure codes, Gaussian basis set is chosen, and for periodic codes, quite often plane waves are chosen. So in FHI-aims, instead, the choices use numeric atom-centered orbitals. And so this is how they are represented in terms of a spherical harmonic YLM plus this U of R, which is a numerically tabulated radial function. So this numerically tabulated bit is where this name NAO comes from. And because they're numerically tabulated, they can have a flexible shape. So in particular, we can account for these little wiggles near the nucleus. And they're capable of describing an all-electron description as well. So we fulfill our criteria of being accurate. As well, we can apply cutoff potential, so that's shown by this black line here, which ensures our radial function is 0 beyond this dotted line here. And this makes the NAOs localizable, which means that they can scale on the order n for most of the computationally expensive steps of the calculation, which makes it scalable. So the second point. And as well, these NAOs can be used for both non-periodic and periodic calculations, so satisfying the final point from the previous slide. And we have a basis set library available with these NAOs in the FHI-aims code, ranging from fast qualitative calculations to converged calculations. And really, we only need a rather compact basis set for converged calculations as well, which is quite nice. Okay, so now that this is the brief philosophy of FHI-aims, I'll spend the next 12 minutes or so just giving an overview of different methods for electronic excited states in FHI-aims. So when we think of electronic excited states, we can broadly categorize them in two ways. So we have charged excitations where an electron can go from a core or valence state to the vacuum, and we can get ionization potentials or binding energies. And we can also have neutral excitations where we promote an electron from a valence state to an empty state. And we have a few different methods in FHI-aims to treat both of these scenarios. So firstly, we have GW, which is for charged excitations, both in molecular and periodic systems. We have the Bethe-Salpeter equation and different flavors of time-dependent density functional theory, so linear response and real time, to describe neutral excitations. And we also have the delta SCF and equation of motion coupled cluster methods, which can describe either charged or neutral excitations. And so in the next slides, I'll just give a brief overview of each of these methods. So first, molecular or non-periodic GW. I won't go into very much detail at all about this since it's going to be covered in much greater detail by Dorothea, as her group is one of the main developers of the GW method in FHI-aims. Just to say, the central idea behind GW is computation of this self-energy sigma, which accounts for the exchange and correlation energy of an electron or hole with surrounding electrons in a multi-electron system. So this is a frequency integration of the Green's function G multiplied by a screened Coulomb potential W. And so this is where this GW gets its name from. And with this, we can compute charged excitations from valence to deep core. And the implementation in FHI-aims can go to around 250 atoms, scaling to the fourth power. We have lots of different options for GW in FHI-aims. So there's different relativistic references, different flavors of GW, from the one-shot G0 W0, where a single GW calculation is done on top of a ground state DFT calculation, to various varieties of self-consistent GW. We also have different methods to do this frequency integration and different post-GW corrections that can be applied as well. And yeah, as well as Dorothea's talk, this will be covered in the tutorial tomorrow for those of you who've registered. In periodic GW, we just have one-shot G0 W0. And a general use case for this is to provide corrections or more accurate band gaps than DFT calculations. So in this figure here, you can see from this implementation paper from Jinggu Ren, whose group also has done a large portion of the implementation of GW in FHI-aims, a comparison between the FHI-aims calculation and a plane wave code, as well as a comparison to experimental band gaps for these materials, showing a good comparison. We also have specialized basis sets for periodic GW and FHI-aims, which will be covered in the tutorial tomorrow. And the method can scale up to around 100 atoms, as you can see in this figure from the roadmap paper, up to 81 atoms for zirconium dioxide unit cell in this case. Okay, so next to the neutral excitation. So the Bethe-Salpeter equation can be used for valence and core excitations. And the idea behind this is you do a DFT calculation from which you can get a screened Coulomb interaction with a random phase approximation. And then you perform a GW calculation to get quasi-particle energies, which are then fed into this BSE eigenvalue equation, in particular in these A and B matrices, which can then be solved to get neutral excitation energies. Oops, wrong way. So for molecular systems, we have both this full BSE equation implemented, as well as so-called Tandankov approximation, where this B matrix is neglected. And this the implementation is described in this paper here from Chiu Liu in Bolkman's group. We also recently have a periodic BSE implemented for just the Tandankov approximation, which is described in this 2025 paper by Ryu Zhu. And here you can see a comparison of the absorption spectrum of magnesium oxide relative to two other codes. So the BSE is also part of the GW tutorial, but won't actually be covered tomorrow, but just so you know, it's in the same place as the GW tutorial. Linear response TDVFT. This is actually quite similar to BSE. So we have so-called Cassidy equation, where this matrix C resembles essentially the same as this A and B matrix that I showed on the previous slide for BSE. The difference is, rather than a GW calculation, you feed into it an exchange correlation kernel. And this is just available for non-periodic systems at the moment with an LDA exchange correlation kernel. And this implementation was also described in this 2020 paper, which had the BSE implementation. And this is mainly work by Jan Kloppenberg and Heiko Abel. And a tutorial for this also appears in the GW tutorial, but again, won't be covered tomorrow as the focus will just be on GW. So we also have real-time TDDFT, where here we're solving the time-dependent Kohn-Sham equation to get essentially electron dynamics properties. And a common thing to calculate, as shown in this figure from this nice real-time TDDFT review, is the time dependence of the dipole moment, which can be used to calculate absorption spectra. And this was implemented by Joska Hekele in his PhD work in Peter Kratz's group. And here you see an absorption spectrum of a K-edge absorption spectrum of water with the FHI-aims results in red and green relative to reference calculation and experimental results. And there is also a tutorial available for real-time TDDFT, which shows how to use it both for molecular systems in the example of the tutorial, the absorption spectrum of water, as well as periodic systems. And you can also do Ehrenfest dynamics on top of real-time TDDFT to get non-adiabatic effects simulated as well. So next, delta SCF. So the idea behind this is that you would do an SCF, for example, DFT calculation of a system with a complete full complement of electrons. And then in this example here, you would remove an electron and do another SCF calculation, in this case a 1s electron. And the difference between two energies gives you an ionization energy for the 1s electron. You can also rather move an electron from this occupied level to an unoccupied level, and then you can get neutral excitations as well. And this table here shows that the keywords that are responsible for this in FHI-aims. So there's actually two different choices you can make, either the delta SCF projector or delta SCF basis, and this table shows the availability of the two keywords. And delta SCF projector, you at the first SCF step constrain an eigenstate to have a particular occupation, and thereafter the same eigenstate is kept with the same occupation. In the delta SCF basis, rather a particular basis function is specified to have a particular occupation, and this is quite useful for example, deep core levels where the eigenstate has essentially contribution from just one basis function. So really, depending on the system you're interested in studying, you choose one or the other of these keywords. And this is mainly implementation work from Rainy Mara's group, as well as Matthias Kapp. And there is also a tutorial for delta SCF available. And this shows how to use the method with both molecular and periodic calculations as well to simulate X-ray photoelectron spectroscopy. The final method that I just want to briefly mention is the equation of motion coupled cluster. So this interfaces to Andreas Grunay's code, coupled cluster for solids, CC4S, via an interface CC-aims. So the idea is FHI-aims would perform a Hartree-Fock calculation from which CC-aims would get eigenenergies, eigenstates, Ri coefficients, and a Coulomb matrix, which is converted into a so-called Coulomb vertex, which is then passed to CC4S to do either these ground state methods, so CCSD, for example, or, as relevant to this talk, the excited state equation of motion coupled cluster. And this can be used for both molecular applications, so for example, this ionization potential of the 5 nucleobases, or for periodic systems in this example, an extrapolation of the band gap of hexagonal boron nitride. And a tutorial is also available on this, and I should say all of this work is the PhD work of Olga Molman, and you can read more about it in these references down here, as well as chapter 4.1 of the roadmap paper. So with that, I think I am out of time. So yeah, thank you very much for your attention, and I'm happy to receive questions now.
Thank you, James, for this very nice talk, this nice introduction into what FHI-aims can do with excited states. And as James mentioned, the Q&A is now open. So if you look into your Zoom toolbar, you will see a Q&A button where you can ask questions, and then we'll redirect these questions to James and try to answer as many of them as we can. If you are watching on YouTube or on Kushare, you also have the possibility to simply ask the questions via those interfaces, and we are also able to see them and ask them in this session here. So please go ahead and type your questions for James in general to this talk. I don't see any yet, but people may still be typing.
I think if we want to say out loud your questions, you can put your hand up, and I think we can unmute you as well.
That's also an option, yes. If you would rather speak directly, you can also raise your hand and we can give you the option to speak. There's a question in the chat. Can you clarify the difference between the two delta SCF options?
Yes, so the delta SCF projector option applies just to a particular eigenstate. So this eigenstate could have many different basis functions that contribute to it. And so the occupation will apply to this state composed of many different basis functions. So will be useful for states that have some contribution from lots of basis functions. The delta SCF basis just applies to a single basis function. So for example, a basis function that corresponds to a 1s orbital. So this is very useful for core states, which just have an eigenstate, which is comprised essentially of one basis function. And yeah, other than that, there are different availabilities of these two methods. So this delta SCF basis can only be used for molecular systems at the moment, whereas the projector can be used for periodic systems as well. Yeah, so those are the main differences between the two.
Thank you, James. I hope that answers the question. Otherwise, feel free to ask a follow-up, of course.
Yeah, I think both of the keywords are covered in this tutorial as well. So for actual examples of these being used.
I mean, one could also add that most of what was discussed is also described in this roadmap. So there are these different chapters in the roadmap. And so if you want to go deeper and also get the original references, which had been on the slides as well, you also find this in the roadmap.
Yes. Thank you, Matthias. That's correct. And the roadmap can be found on archive. Maybe we can also post it again in our chat box.
Mm-hmm.
Any other questions on this part? There's a question from Hyung-Yong Kim. Can delta SCF be used in excited state calculations?
Yes, I mean, delta SCF is used to essentially compute excited state energies and can be used in either the charged excitations case or the neutral excitations case. So, for example, in this case, in this example here, just an electron, this SCF calculation, this second one, was computed with just an electron removed. So this would be for the computation of, say, this ionization energy of the 1s level. So this is a charged excitation. But we could also, rather than removing this electron, just put it in a valence state instead. And so then you'd get an absorption energy or neutral excitation.
Yeah, thanks, James.
And I still would add to that this is one choice and a cheap choice, but the better choice is what really Dorothea will discuss in the next talk. Right?
Yes. Then we have another question. And the question is, how are the numeric radial basis functions UI calculated?
Okay, yeah. So we have different options for these. So there's hydrogenic functions or ionic functions, and they're essentially tabulated based on the orbitals that they correspond to. Maybe Volker can chime in with more of the exact details.
Yes, we can do. But in short, they're calculated as radial functions from a numerical solver for spherical potentials. So, for example, a free atom potential for the minimal basis, but the free atom will be spherical, so the electron occupations will be chosen such that the atom is spherical. And so this is essentially what Hartree, in a way, already introduced in the 1927s, although this has advanced in terms of what it does numerically and stability and so on. But these solvers are very well established. And so that's how we calculate the atomic solutions, also the hydrogen-like solutions, also ionic basis functions. Additionally, we can calculate, of course, Gaussian basis functions as Slater-type orbitals, and those are just tabulated from their analytic formula. So Gaussians are Slater-type orbitals which exist because we do reference back to those methods, are just calculated analytically.
Thank you, Volker, for the added details. So hope that also answers this question. Okay, we still have time for one last. Okay, there's another one. In the delta SCF approach, to calculate the binding energy with the difference of total energies, are the separations of the levels kept the same? For instance, if the order of the levels is changed after the SCF, the resulted excited state won't be the one we want to observe.
Yes, so the delta SCF projector method has this maximum overlap method implemented in it. So the idea is that the state that you choose at SCF step 1, even if it changes order later in the SCF, it still is kept as being the one you want to fix the occupation of later in the SCF. So essentially the idea is you need to know, or you would say do a full SCF calculation and you know the state you want at the end, and then you kind of try and work out what state it is at the first SCF step. And even if they're different, you would just choose the state in the first SCF step, and this maximum overlap method should keep it the same to the end.